want to talk about identity and inverse matrices. We were doing an investigation in class that led us to these ideas, but didn't have time to really summarize the punchline, so this will just hopefully be a short one. Let me go ahead and look at a little bit of a different system of equations, just so we can see another example. Suppose we're solving this system of equations. And we can put that in matrix form by taking the coefficients and putting them in a 2 by 2 matrix. 4, 11, 2, 6. Whoops, that's weird. There we go. Put the variables in a column vector and put the coefficients on the right hand side in a column vector. And so we often call that AX equals B. And we discovered that, at least for another 2 by 2 example, there was a magic matrix that somehow was created out of these 4 numbers, and we'll talk about that in a second, so that when we hit both sides of this with that matrix, the left-hand side, it kind of just evaporated this guy. It made the A disappear and just turned it into XY. And so let me go ahead and give you that matrix in this case. And I'm going to go ahead and give you the official name for it. It's called A inverse. And we'll see why it's called that. So I'm going to copy this so I can get a 2 by 2 matrix. Turns out that if I do this, look at this matrix, 3 minus 11 halves minus 1, 2. Then let's see what happens if I multiply both sides of this equation by this matrix. So let's set that up. I'm going to take this guy. That's not what I meant to do. Control C. Control V. There we go. Okay, I'm going to multiply both sides of the equation by the same matrix. Okay. Now, it looks like a big mess, but the right-hand side is just a matrix times vector calculation. That's not a super hard thing to do. You have to get used to it. We're still getting used to the idea of how to multiply all these guys. But the rule is relatively straightforward. And so let's do that. It's going to be, I'm going to write it out, 3 times 4, whoops, times 4, and then minus 11 halves, put that in parentheses, times minus 3. This row kind of rotated and matched with that column. And then minus 1 times 4 plus 2 times a minus 3. And so that's just going to be, let me get another 2 by 2 matrix going here, or rather a 2 by 1 matrix. Okay, so that's 12 plus 33 halves, so that's 24 plus 33, 57 halves. And then this is minus 4, minus 6, and minus 10. So the right-hand side is a pretty simple calculation. And let me summarize it. It's equal to A inverse times B. That's what we did. We took this funky matrix, which I claim deserves to be called A inverse, we'll talk about that in a minute, and times B. So the right-hand side is pretty simple to do. The reason that's interesting, like why the heck are we doing that calculation? The reason that's interesting is that I claim this matrix has the same magic power to take this whole thing and just create XY. And if we just see XY here, then and XY is going to be equal to 57 halves minus 10, then we're done. X is equal to 57 halves, Y is equal to minus 10. Why would that work? Well, as written, what I've really done is I took this AX, which was the left-hand side of this equation, and that I'm thinking of as sort of you calculate that first, and then only after that you bring in the A inverse. Well, but you know what? I've claimed that matrix multiplication is associative, and it is. It's not something we're going to prove, but it's not too hard to prove. And so I can actually write it in this way, and that turns out to be super useful, because the product of these guys is a very, very simple matrix. So I'm just going to copy this guy. It hasn't been multiplied in yet. And the product of this guy is 3 times 4 is 12 minus 11 halves times 2. 12 for the 3 times 4, and then minus 11 is 1. Okay, so let's actually start to build this matrix. 3 times 11 is 33, minus 11 halves times 6 is minus 33. That's a 0. Very simple. Minus 1 times 4 is minus 4 plus 4 is 0. And minus 11 plus 12 is 1. So what's so special about that? Why is it so interesting that we get this matrix? It's because this is a very, very special matrix. This 2 by 2 matrix times any column vector gives you just that column vector back. And in fact, this 2 by 2 matrix times any matrix just gives you that matrix back. So 1, 0 paired with xy just gives you x, and 0, 1 paired with xy just gives you y. And indeed, I've got x, y. So summarizing, what did we do here? We had ax equals b, and then I multiplied it by A inverse. And I grouped these together. And so I didn't really, all I did was multiply these guys together. On the left-hand side, I got a very special matrix. And so we talked briefly in class about how this matrix has a name. It's called the 2 by 2 identity matrix. IX, or if you want to be really explicit, I sub 2, because it's just to make us aware that it's the 2 by 2 identity matrix. And the special property of this identity matrix is that that times anything is itself. This wouldn't have been useful if I brought in a new matrix, multiplied it on both sides, and I got something even more complicated, or something just as complicated as I started. But I2 is so simple that it just goes away. And we just get x equals A inverse times B. And so that's really nice. It's really nice to have this A inverse. So the summary is that an identity matrix like I2 is this guy. I'll just pick it up from here. 1's on what's called the main diagonal, 0's everywhere else. I3, that's very similar. 1, 1, 1, and 0's everywhere else. And what's special about that is that if I multiply it by anything, I times x equals x, if x is a column vector. I times b, another column vector. I times any kind of matrix. Doesn't matter what it is, as long as the product is defined, it's equal to itself. And in fact, we haven't used this in this particular use of it, but even if you multiply it the other direction, it's equal to itself. That's something you can test by just multiplying this matrix by a few matrices, and you start discovering that it has this wonderful property. So it is the analog of the number 1 in ordinary algebra. What's so special about the number 1 is that 1 times anything is whatever you started with. 1 times 5 is 5. 1 times 9 is 9. 1 times x is x. Okay? So that's the identity matrix. And then the inverse matrix, this thing A inverse, that its role is that A inverse times A just gives you back the identity matrix. That was super nice. In this example, these two guys basically annihilated each other to produce the simplest possible matrix, which then just goes away, and we're left just with x and y, unmixed, without any coefficients, and suddenly the answer is staring at us. And so, in fact, to be really precise, A inverse times A and A times A inverse turns out to really qualify as the inverse. You want to be able to do it in both directions. Usually you don't have to worry about those separately for numbers, because it doesn't matter what order you do things in, but for matrices it usually matters. The great thing is that if you've got an inverse matrix, in either order you multiply the matrices, you actually get the identity matrix. There's some subtleties about that which we totally will not discuss, but that's something to note. Okay, so that's why this thing did its magic. Now then the question is, somebody asked this in class, how did you get this? What's the formula for this guy? If we had a magic formula for this, it makes solving equations, or it gives another way of solving equations. I won't claim it's really easier, but it's another alternate way. Well, the inverse of a 2 by 2 matrix, I'm going to give you the master formula. It's just not something we have time to derive, unfortunately. The inverse of this guy, actually, let's see if the calculator can do this. curious. Ooh, there we go. Smart computer. It's a little complicated looking until you look and you see the denominators are all the same. And so, in fact, what we can do is we can just take that out. Remember, you can always multiply a number times a matrix. And I'm just going to change this to a D. Just change this to a minus B. Change this to a minus C. And change this to an A. And so what you do is you just fiddle with the coefficients here, and then you divide by this magic number. And this magic number, the AD minus BC, I'll just go ahead and give you the name for that. That's the subject of our next section. The name for the quantity AD minus BC is the determinant of the matrix A. And that's going to be, that has a lot of interesting properties. So here's the rule. You take A and D and you switch their positions. You swap them with each other, but you don't change the signs. B and C, you don't change their positions, but you do swap the signs. So that's a little interesting. And then you divide by this magic number called the determinant, AD minus BC. One thing that tells you, or that the question that suggests, is what if AD minus BC equals 0? Well, in fact, such a matrix, it's not just that you have to use a difference formula, it's such a matrix has no inverse. There are plenty of matrices that have no inverse, and the reason we could have actually sort of predicted that, it's related to the fact, very closely related, and we'll talk about it, that not all systems of equations have solutions. Well, I'll tell you, just half a minute more, I'll just tell you. If we go back to this method, we start out with, let me put in an extra line here, AX equals B. Suppose we could always do this. Suppose we could always find the inverse. We could always do these steps, and we'd say, oh, X is A inverse B. There's one and only one solution. It's A inverse times B, just gotten by a matrix multiplication like we did here. But we know that doesn't always work. We know we can set up systems of equations that have many solutions or that have no solutions. So this can't possibly always work. Well, where it goes wrong is A inverse might not exist, and therefore none of this makes any sense. And that's going to be a very important thing to remember, is that lots of matrices have no inverse. For a 2 by 2 matrix, it's easy to figure that out. AD minus BC is the test for that. Okay. What about 3 by 3 or higher matrices? And the truth is, the formulas get pretty complicated for the inverse. And that's one thing why this isn't the killer method that everybody always uses to solve equations, systems, because in fact the formula for the inverse is somewhat complicated. It's known. There's a procedure for it. But we're not going to emphasize it a lot because it's complicated, and we'd probably want to be able to spend a lot more time on it. Okay, that's all I needed to say, and then there's a few homework just basically on the very basics about inverses.